We continue today with our discussion of bosonic particles in solids and more generally condensed matter. And today we talk about lattice vibrations and phonons. Phonons, which are the quanta of lattice vibration, are perhaps the most quintessential of emergent bosonic particles in solids. And again, this is something that maybe many of you seen at least some discussion of phonons in some undergraduate or statistical mechanics course previously. So I will kind of go through this relatively quickly through the elementary things and then point out some things that you may not have seen. So I start from a very simple one-dimensional model of a solid, which is just a bunch of ions, all with mass m, connected along this 1D line by a bunch of elastic springs. And each of these springs will be characterized by just the force constant k. Now, let's start a little more generally, and let's write down a generic one-dimensional Hamiltonian for a system like this, masses and springs. So we have our kinetic energy, and then generically we have some potential energy V here, which we can write down easily if this is just a bunch of elastic springs. But more generally, I think it's useful to start from a generic potential that could occur in some solid, which, this is just a cartoon of. So the way one proceeds is as follows. One wants to expand this general many-body potential in small vibrations around the equilibrium positions. And this is what the theory will do well. It will describe small vibrations around equilibrium, and we will show that these can be treated exactly. So exact solutions are available. So we expand, assuming small displacements. And we expand this potential as follows. V y1, yn. We write it as V at 0, 0, 0, meaning we're expanding around some equilibrium position when there is when the lattice is undistorted. That we denote by everything being at 0, and then we just do a Taylor series in these displacements. And this is the first order term, and then we proceed to the second order term. Okay, and we stop at second order, but it's obvious how this would proceed. It's just a Taylor series, although we're expanding in many variables, so that's why the structure looks like this. Now, if you look at this, you can see that this term here, the first order term, should vanish because in equilibrium, if we define our position 0 for all variables as the equilibrium of the system, then this is how we define equilibrium, right? In equilibrium, no forces should be acting on our masses, and this gradient of the potential is just force. So in equilibrium, we can neglect this term. And the first non-trivial term is this one. If we retain only terms up to second order, then that's known as harmonic approximation. And in harmonic approximation, it will turn out that we can solve the problem exactly for arbitrary arrangement of masses and spring constant. So basically, what we're doing, we're taking this arbitrary potential, and near its minima, we're approximating it by a bunch of parabolae to second order here. Any questions about this? Okay. So in the following, what we will do, we will, well, this term is 0 by definition, and we will also neglect this first term, which is just a constant, so we can redefine the overall energy. So all we have is this momentum term and our harmonic term that we wrote down here. Okay, so let me now specify this momentum term. Here, by momentum, we mean the usual quantum mechanical definition, IH bar d over dyl. And this then implies the usual commutation relation between coordinate and momentum. This is just IH bar delta LL prime. This is how momentum is always defined in quantum mechanics, and it leads to that commutation relation. Now, what I will also do, I will write this potential term in a somewhat simpler fashion so that the whole Hamiltonian, okay, let me write it like this. In the harmonic approximation, we then have the following Hamiltonian. I just copy the kinetic energy term. Okay. So I'm simply denoting this whole thing together with the factor of 1/2 as V, or let me write it like this. This is 2VL L prime, and this object here is often called a dynamical matrix. Of this type of a system. And the reason why it's called a matrix, well, it depends on two discrete indices, so it can be viewed as a square matrix with matrix elements V L prime. And this becomes even more obvious, and we will use this matrix notation. We can write this potential term as follows. If I imagine organizing these displacements into an n-component vector, then this expression here can be written as a matrix multiplication, as you can imagine. Okay, and in what follows, I will call this a n-component vector y. This thing here will be y transposed, or since it's a real vector, I can as well write it as y Hermitian conjugate, and this will be my matrix V. So this expression is simply y dagger V y, and you can now see what follows. Solving this Hamiltonian is equivalent to finding a transformation that diagonalizes this dynamical matrix. So I want to find a unitary transformation U that diagonalizes my dynamical matrix V. Okay? Unitary matrix means that U dagger U gives me unit matrix, as well as U dagger is equal to U minus 1. Okay? And the matrix needs to be unitary in this case so that we preserve the canonical commutation relations between the momenta and the coordinates, as I will ask you to check. Okay, any questions about this? So basically what I will do, I will take this term, right? I will write it as I indicated, Y dagger Vy, and then I do the usual thing. I will insert here a unit matrix resolved as U dagger U, as well I will insert here a unit matrix resolved in the same way, and write this as follows. This is going to be U, Y, dagger, U, dagger, V. Sorry, it should be like this. U dagger, U, Y. Okay. And of course, I'm choosing this transformation such that this matrix is diagonal, and I will call these individual quantities as Y tilde, and this I will call as V tilde, and these guys are diagonal. So after this diagonalization, what I get here is Y tilde, V tilde, Y tilde, but this matrix now here is diagonal. And if I want to, I can then write this simply as sum over Q, Y dagger Q, YQ, VQ. So here I have just taken into account the fact that this matrix is diagonal, right? So when I perform this multiplication in that basis, I only have diagonal terms. I only need to sum over one variable over all the diagonal terms, and that's what I get. Any questions about this? Okay, so this type of operation diagonalizes my potential term. What I have to now ensure is that when I do this, I don't mess up my kinetic energy term. Now this one is already diagonal, right? Because it does not have any off-diagonal terms. It's just PL. And in fact, if I were to write this term in the matrix form, then you would see that it's basically the corresponding matrix for momenta would just have 1 over 2m on the diagonal and zeros everywhere else. So it's proportional to a unit matrix, and it's obvious that under unitary transformation, unit matrix does not change. So this term indeed should not change under this transformation. One thing that I would like to point out is that because PL is defined in this way, so there's an inverse of this Y of L. Actually, the way momenta transform is not like this, but they transform in the opposite way. So coordinates transform as Y tilde is Y, U times Y, but momenta transform as Y tilde. Actually, they transform as U. P tilde should be U dagger P, and I ask you to check this. It's just a simple consequence of this definition. And if you don't see that right away, I ask you to please check that. And also, when you perform that transformation, you find that the new transformed operators satisfy the same commutation relation. So what this leads to is y tilde q, p tilde q prime. They satisfy the same commutation relations, I h bar delta q q prime. And I also ask you to check this as well. So what this means is that for an arbitrary dynamical matrix in harmonic approximation, we can solve this problem, right? Well, as long as we have sufficient resources to diagonalize an n by n real symmetric matrix. So if it's some hugely irregular problem and the matrix is very big, then it may take a long time to numerically diagonalize that, but we will see that, for instance, for a translation invariant situation like this, when all the masses and all the spring constants are the same, we can just do this by hand. And I will show that in a moment. Before I do, it's useful often to perform one more step. So now our Hamiltonian is diagonal. So we write it like this. Sum over Q. 1 over 2m. The kinetic energy has not changed. P dagger Q, PQ, plus 1/2 m omega Q squared y dagger Q, YQ. And I put I put these tildes on to make sure that these are the new coordinates. This omega q I have defined as being a square root of VQ over M, and these will become the phonon frequencies. There's one more step that is often useful. So what you can see that this is nothing but a collection of independent harmonic oscillators, right? It is often useful when you have a bunch of harmonic oscillators to go to a representation with raising and lowering operators, because there everything becomes even more obvious. So let us do that. For each linear harmonic oscillator, we define the appropriate raising and lowering operators, and we define them in a usual way. AQ is defined as 1 over square root of 2m h bar omega q m omega q y tilde q plus I P Q tilde, and A dagger Q is just the Hermitian conjugate of this, which will only affect this part. Like so. And in these coordinates, the Hamiltonian simply looks like this. And hopefully everybody has seen the basic lore of harmonic oscillators. So basically, once again, if somebody gives us a dynamical matrix here, and we're able to diagonalize it and find frequencies, then that transforms that system of many coupled masses into a system of decoupled harmonic oscillators. And that's a generic property of such quadratic systems. We can always solve them with a moderate amount of effort. Okay. Any questions about this? So let's consider a case which is of interest in condensed matter physics, namely when we have a lattice in 1D that would be just a periodic chain of masses and springs. And in that case, we can actually solve the problem to the end by hand. Namely, we have a translation invariant system, and what this means in terms of these objects is that VL, L prime, simply depends only on the difference between the two, and the potential term then simply has a form that looks like this. Okay. And in this case, what one expects is that the way to diagonalize this type of Hamiltonian is to go to Fourier space, right? Anytime that you have a periodic structure like this, it's always useful to go to Fourier space. So let's try that. Namely, we choose our unitary transformation as follows. UQL, we choose it as 1 over square root of n for normalization, e to the I QL. And if this looks mysterious, that's equivalent to writing y q tilde as being 1 over square root of n sum over L e to minus IQL y of L. And similarly for momenta, PQ tilde is 1 over square root of n sum over L e to plus IQL times P of L. So this is just the unitary transformation. And from now on, I will refrain from writing these tildes because they are somewhat ungainly. So I will, as usual, distinguish between variables in real space and momentum space by distinct indices. In one case, it's going to be Q. In another case, it's going to be L. Okay, so before we go ahead, let's just do some housekeeping. So first of all, we need to worry about the boundary conditions when we're doing transformations like these. And in condensed matter, we always, or most of the time, use periodic boundary conditions. Namely, we impose that y shifted by n times a, where a is the lattice constant, goes back to YL. So that corresponds to identifying the first with the last of our masses. And like I said, the distance between the masses will be a lattice spacing. And this has an important implication for the allowed values of these momenta, because if I translate this, what that means in here, that simply means that e to the iq times L is equal to e to the iq L plus NA. Yes?
So if coincidence that you were using a Q or the Q subscript all the time when we diagonalize the elements?
Well, it's just when you do Fourier transform, you usually call momenta Q. So here, it's not a coincidence. Here, I should have been using some more general letter maybe. But so what I wanted to emphasize here that this method works for any system, does not need to be translation invariant. It's only useful to Fourier transform when you have translation invariance, right? So in that case, those Q's become one-dimensional momenta. More generally, in this case, these should not be viewed as momenta because that transformation might be, if you're discussing, say, normal modes of some complicated organic molecule, there's no translational symmetry, so this transformation will not be in general Fourier transform.
Okay, so now that we're using the Fourier transform, it's going to end up to be diagonalized the matrix.
Yes, exactly. Okay, so again, periodic boundary conditions then require that this condition is satisfied, and what this means is that these momenta Q are only allowed to have the usual values. Q is 2 pi over A times n over capital N, where n is an integer. Okay, and that's just because I can cancel out e to the iql from both sides, and then I'm left with the condition that 1 is equal to e to the I q n times A, and this condition is only satisfied when I take these q's of that form. And also, what I get from this, and again, this is just the basic lore of periodic lattices, is that y of q in momentum space is always equal to y of q plus g, and similarly for p, where this g is 2 pi over A, and it's just the usual reciprocal lattice vector. And what this implies is that Q then ranges between minus pi over A to pi over A. All the independent values are in this interval, because when you shift by any number of reciprocal lattice vectors, you get back, according to this condition, you get back the same displacement. And this is nothing but the first Brillouin zone. Okay. So let me continue here. Let's now show that indeed this transformation diagonalizes the system, that the Fourier transform diagonalizes the system in this case. So let's write this. V tilde Q prime, according to our definition, is just U dagger V U matrix element Q prime. And this, when I plug in the matrix element, will just be sum over L prime of e to minus I QL V L minus L prime e to I Q prime L prime, right? So all I'm doing, I'm just using that definition of U to plug this in. and writing everything in components. 1 over n comes from, again, the definition of u. And now, because v is only a function of differences, that's translational invariance, in this sum, I can shift my l's such that I only have one L here in the argument. So I can do, for instance, L goes to L plus L prime. These are dummy summation variables. And what I get from here is 1 over n sum over L prime e to minus I L prime q minus q prime, and then I'm left with sum over L e to minus I QL VL, and I identify this as V of Q, just the Fourier transform of Q, and this guy here is nothing but delta Q Q prime, so I conclude that this is delta Q Q prime V of Q, and indeed this is diagonal because of this delta. That delta is a unit matrix in Q space. Okay. So this shows that indeed for arbitrary translation invariant system, Fourier transform, as expected, diagonalizes my dynamical matrix, and I get something that is now diagonal. Okay, so at this point, I can do the, so my Hamiltonian is now diagonal, and I can perform this final step where I write it in raising and lowering operators, but that's going to be precisely the same as before, so I will not really rewrite it. One can just follow this prescription here. Okay. So let me just write here in words. Indeed, Fourier transform diagonalizes VL minus L prime for translation invariant system. Okay, let us proceed with an example. And this is the simplest example that you can conceive of, which is basically what I drew up there. So I have masses m, spring constants k, and they are all the same. So it's just a uniform one-dimensional chain. In this case, I can write this potential as follows. So this is the full potential. And it looks like this, 1/2 k y L minus y L minus a squared. Okay, it's just if I have a bunch of springs, it costs me k to deform them away from equilibrium, 1/2 k by definition. And the way to proceed, so what I want to get a dynamical matrix from this, right? And I can either take two derivatives, which would be, however, overkill here because it's just a quadratic function. So I can simply reorganize this. I can develop this a square here, and I can just write it like this. I can write it as sum over L 1/2 k times 2yl squared minus 2yl yl plus a. Okay, and you see what I did. I squared this, squared that. This is the mixed term, and when I square that, I just shift by a, so I get that term twice. Okay, and that's easier. But the nice thing here is that from here, I can right away read off my dynamical matrix, right? And the dynamical matrix looks like this. V L L prime is equal to 2k if L is equal to L prime, right? And is equal to minus k if L is equal to L prime plus minus A, and is equal to 0 otherwise. Let me maybe write it in a nicer way here. Okay. So if you imagine this written as in a matrix form, then on the diagonal I will have 1/2 k times 2. Okay, that would be on the diagonal because that has a term that is YL squared. And then on the off diagonal, I will have these two terms. I will have these mixed terms whenever L prime is equal to L is equal to L prime plus or minus A. That's just this term. But there's two of those terms, one above diagonal, one below, and that's why I just take that once, whereas here I have that twice because I have only one term for each L on the diagonal. Okay? And again, if this is not clear, I encourage you to explicitly write down that dynamical matrix from here. Or one can just start taking derivatives and get this explicitly according to the prescription. Okay, so now we have translation invariant system. To get our diagonal Hamiltonian, let's do the Fourier transform. So here, there's V of Q. So basically what I'm doing now, I'm calculating the V of Q. Okay, V of Q will be sum over L e to minus IQL times V of L. Okay, and I can explicitly calculate that because most of the terms in my dynamical matrix are 0, right? The only term when the only time in this sum over L when this term is not 0 is when either L equals L prime or they differ by plus minus A. So I can write this right away. I get 2k, which occurs when which comes from this diagonal piece, and then the off diagonal piece gives me minus k e to I QA plus e to minus I QA. Okay, so this comes from here, and again, these exponential terms acknowledge the fact that this is only non-zero when L differs from L prime by plus or minus A. And now I can simply rewrite this as 2k times 1 minus cosine Q times A. And if I want to, I can use the trig identity to write this as 4k times sine squared QA over 2. Okay. Now this allows me to get my frequencies. Frequencies are related to these Fourier transformed diagonal elements of the dynamical matrix through a square root. Well, first I divide by m, then I take a square root. So omega q is VQ divided by m. And here it is useful that I have used this trig formula because I can take this square root easily. And what this becomes is 2 square root k over m times sine QA over 2. And this is the classic result for a dispersion of a one-dimensional, a simple one-dimensional lattice with just nearest neighbor springs. So let's plot that. I'm plotting in the first Brillouin zone minus pi over A, pi over A. This is the Q. This is omega Q. And it looks like this. Okay, well, it should be symmetric. I didn't quite manage to draw it symmetrically, but it's just that formula over there, absolute value of sine Q over A, sine QA over 2. One thing that is to be noticed here is that at small value of momenta near 0, these can be approximated by just straight lines. And here, along this straight line, omega Q is simply C times Q. So we identify these as sound modes or acoustic modes. Okay, because we know that sound dispersion in either a solid or a liquid has this relation between frequency and momentum, which is just linear, and this is valid at long wavelengths, where basically you can describe this solid as a continuum elastic material, and indeed that is borne out from this detailed microscopic calculation. Any questions about any of this? So in a solid, this is usually not all there is. We consider the very simplest possible model. If you had a more complicated structure, such as a chain with different types of atoms, say atom A and atom B, that have different masses, then this solution would be slightly more complicated. And what would you find is that you would find, in this case, for masses M1, M2 that are different, you would find that there's actually two different modes that are solutions of these equations of motion. And in addition to an acoustic mode that looks like this, there would also be some other mode here at higher frequency, which in condensed matter physics, we call these optical modes. And this is a generic property of more complicated lattices. In one dimension, there will always be precisely one acoustic mode, because there's just one sound that is propagating. But there can be many optical modes. Namely, if you had a diatomic chain, there would be just one. But if you have n different types of atoms in your chain, generically you would always have one acoustic mode and n minus one optical modes. So for n different masses, there would be one acoustic mode. Namely, it would have a property that for small frequencies, the frequency is proportional to momentum with some speed of sound, and it goes to 0 at 0 momenta, and n minus 1 optical modes that generically will be at higher frequencies, and they don't go to 0 anywhere in the Brillouin zone. And in the next tutorial, I believe not today, but on Wednesday, you will get to solve the problem with, of diatomic chain with two different masses. So you will see actually how that arises in a specific situation. Okay, any questions? So now let's move to three-dimensional lattices. And let me just say that the strategy that we employed in 1D works equally well in 3D, but unfortunately everything becomes a bit more messy because in 3D, first of all, you have atoms or ions organized in some three-dimensional fashion in a 3D lattice, and also they can oscillate in three independent directions. And one has to, one can go through this whole calculation, but one has to add some additional indices that take care of this more complicated structure. So what I will do here, I will outline how this goes, and then just point out some main features or how is this different from a simple 1D case. But I will not do that in a great detail because basically all the ideas that are there already appear in one dimension. So here we have some three-dimensional lattice, which I will represent by this two-dimensional sketch of one layer of a cubic lattice. And its individual ions will be denoted by now vectors L from some origin. And these vectors L take the form of N1 L1 plus N2 L2 plus N3 L3, where these N's are just integers and these L's are primitive lattice vectors of this Bravais lattice. And then the Hamiltonian for the elastic solid can be written like this. I have to now sum over these positions L as well as over Cartesian components of our momenta. And it looks like this, PL squared over 2m. Again, in the simplest situation, I'm considering the case when all these ions have exactly the same mass m. But of course, in a more complicated solid, these can be many different types, and then it's becoming even slightly more complicated. And then I write my potential term, but I only keep the term up to harmonic approximation. And I will get L, L prime, I, and J. And it looks like this. Y, I, L, Y, J, L prime, VL, L prime, I, J. So now, and then there will be some additional terms, cubic, quartic, and so on, which I'm neglecting in my harmonic approximation. So it looks just like before, except that I have these additional indices I and J, which denote the Cartesian coordinates of the displacement, right? This atom can be displaced in three independent directions, and so these indices I and J stand for x, y. I and J stand for x, y, and z. And also these L's are vectors because they label these three-dimensional positions in space. So the Hamiltonian looks the same, but it's somewhat more complicated. And the dynamical matrix Vij, L, L prime, has a definition that is similar to what we had before. It looks like this. Okay. So now, and let me focus in this case in 3D, we will focus on translational invariant situations, as I already, well, this already implies translational invariance. So we go through the same steps. We perform a Fourier transform, and this is done like this. Y Q I is 1 over square root of n, sum over L e to I Q dot L, Y I L, and similarly for momenta, P I L is 1 over square root of n, sum over L e to plus Q dot L P I L. And again, in 3D, under periodic conditions, also I have periodic boundary conditions, and allowed values of Q have that form, but now I have 3 independent components. And also I have this property that I have reciprocal lattice vectors, but now they are vectors. So I hope I don't need to rewrite that. And when I perform this Fourier transform, then my Hamiltonian can be written as follows, and I will just emphasize a few things that are different compared to 1D case. So I have sum over Q, and here I have 1 over 2n. So I have, again, my kinetic energy term remains diagonal. That doesn't change. And then I have my potential energy. And here's a bit of a difference compared to 1D case. So here's a bit of a difference. Let me erase this so that you can better see this better. So whereas previously in 1D, when I performed the Fourier transform, I was done because my Hamiltonian was diagonal. In this case, because my atoms here can oscillate in 3 independent directions, I'm left with this 3×3 Hermitian matrix that I still need to diagonalize. Okay. Now, if I started from a more complicated lattice structure, such as Bravais lattice with 2-point bases, then this would end up being a 6×6 matrix. With in a Bravais lattice with n-point bases, this would be a 3n times 3n matrix, but still it's a finite size matrix which one can diagonalize. Now, in general, if we just focus on this case of a 3×3 matrix, it will have 3 eigenvalues. It's a Hermitian matrix, which I will denote as V1, Q, V2Q, V3Q, and also three independent eigenvectors which can be chosen as mutually perpendicular. And they are typically denoted by S1Q, S2Q, S3Q, and they can be taken at, well, if these eigenvalues are distinct, then they are automatically perpendicular to one another. If there is some degeneracy, one can choose them as being orthonormal. That's just basic theory of Hermitian matrices. And what I maybe forgot to mention, let me put it here, this object here, V of Q, is of course just a Fourier transform. So VQij is sum over L e to IQ dot L V ij of L. Okay. So now suppose we have diagonalized this 3 by 3 matrix. We found its eigenvalues, its mutually perpendicular eigenvectors. We can then rewrite everything as follows. So after we diagonalize that matrix, then it can be written in this form where these y's with superscript mu are defined as a y vector dotted into, well, basically it's y vector written in the basis defined by these three eigenvectors of my dynamical matrix. Okay, so in this case, the Hamiltonian is fully diagonal. So this is diagonal now. And we're using the same principle as before, that a unitary transformation applied on this does not change the momentum part, because that is already proportional to a unit matrix. Finally, we define the corresponding frequencies. And again, mu is 1, 2, and 3. So it should not be surprising that since these atoms can oscillate in 3 independent directions, we find 3 distinct frequencies now labeled by this quantum number mu equals 1, 2, and 3. And we can also go to the basis with raising and lowering operators. We define them as before. AQ mu is 1 over square root of 2m omega q mu m omega qm yq vector plus I p q vector dotted into SQ mu. And similarly for A dagger Q, but I will not write that because everybody can take a Hermitian conjugate of that. And in this representation, the Hamiltonian finally takes the form that is familiar to everybody, hopefully. So again, we arrive at, in this case, 3n independent oscillators. Okay. Yes, question? Yes, there should be a dagger. Thank you. So now that we laid out this general formalism, let's do something that is more physics than just manipulating equations. And let's discuss something that is actually physically measurable. So this theory, if it has any validity, it should have some measurable consequences. And yeah, let me move to the other side here. And the most obvious of these is phonon-specific heat. This is something that has been measured long time ago, and it presented some mysteries to classical physics, which was before the advent of quantum mechanics, which was all that people knew, of course. So let's discuss phonon-specific heat. In a solid, typically most of its specific heat is stored in lattice vibrations. When you're heating up a solid, whether it's a metal or an insulator or a magnet, typically most of the heat is then stored in these lattice vibrations. In the metal, some part of it goes to electrons, but that's typically negligible at, say, room temperature. And so let's try to understand that. So we start from that Hamiltonian over there and calculate the specific heat that is stored in those oscillators. And let's start by evaluating the internal energy corresponding to that Hamiltonian H. This is U of T is just the thermal expectation value of our Hamiltonian. And this we calculate simply by calculating the expectation value of our bosonic operators that we introduced. Right? And these guys can be shown to satisfy the usual bosonic commutation relations. And I haven't written that, but let me write it down now. AQ mu, A dagger, Q prime, mu prime is simply delta Q prime, delta mu prime. So these are bosons. And one can show that simply, we know what these guys satisfy, right? That's been written up there. These are the usual position momentum commutation relations. So you can just plug in these definitions into the left-hand side of that commutator and check that this is indeed the case. So the expectation value of this product, this is just a number operator, should be given by Bose-Einstein distribution function then. And let's just write this down. So this is just n of q and mu in this case. So let's write that out explicitly. This is going to be sum over q mu. And we can write it like this. H bar omega q mu. Now, also notice, so this is just the Bose-Einstein distribution, as I mentioned. Notice that I'm not putting in any chemical potential, and I'm not putting in any chemical potential because these kind of emergent bosons, their numbers are not conserved. And if you recall back in statistical mechanics, how chemical potential is introduced as a Lagrange multiplier that allows for enforcing the conservation of the number of particles. Since these particles are not conserved, I don't have any chemical potential here, so that's what is different from these fundamental bosons. Now, so this is an expression that one could evaluate, and we're not really interested in the internal energy itself. We're interested in the specific heat or heat capacity. And the specific heat is usually denoted by CV and is defined as du T dt. Temperature enters through this beta parameter, so we can take a derivative of this expression and write it in the following form. It's 1 over kb t squared sum over q mu. And the expression looks like this. E to beta h bar omega q mu minus 1 squared h bar omega q mu squared e to beta h bar omega q mu. And let me put a... So now, in order to proceed from here, one would think that one would need a specific model for these frequencies, right? I cannot really perform this summation unless somebody tells me what should I put in for those frequencies. So, you know, in principle, I should just consider some specific solid, solve for its frequencies, and then plug them in. However, there are some generic features of all solids that can be modeled without such a level of detail, and this comes from the so-called Debye model, which was the first successful model to calculate a specific heat of a solid that was in a reasonable agreement with experiment. It is interesting to note that the Debye model was preceded by the so-called Einstein model due to Einstein, which had some redeeming features, and I will mention it in more detail if we have time, but it didn't quite work. So even Einstein sometimes is not right, and Debye then came up with a better model, which actually is used up until today, and this was formulated early on in the early days of quantum mechanics. So the way it works is the following. We define a quantity known as density of states, and for the Debye model, or for this situation, is defined as a function of variable omega, which looks like this, q mu, and is a sum over a delta function of omega minus the actual frequencies. Okay. And once we define our density of states like this, we can rewrite this expression in the following way. Cv is 1 over kb t squared integral from 0 to infinity d omega h bar omega squared e to beta h bar omega divided by e to beta h bar omega minus 1 squared times this d omega. And you can check that indeed this is true, because if you plug this back in and perform the integral over omega just from the properties of the Dirac delta function, you immediately get back to this, right? Now so this expression looks kind of vaguely simpler, but all that we have done, we have shoved all our ignorance of these eigenvalues of frequency into this d. And Debye noticed that there is some nifty approximation for that d that one can use and get some useful answers that are valid for solids in general. So, so what Debye did, found a suitable approximate form for this function, the omega, that corresponds to the density of states. And here's what he said. He said the following: if we're interested mostly in low temperature behavior of this function, this is where historically there was the biggest discrepancy between classical physics, which predicted that specific heat should go to a non-zero constant, and the actual measurement, which found that specific heat of all solids just goes to 0. So that's where the discrepancy was that Debye was trying to solve. So at low temperatures, basically you just need to accurately take into account the low momentum behavior of these frequencies, long wavelength behavior, because that's where, so in other words, the acoustic modes up there in that picture should be most important at low energies, right? Because only those will be activated when temperature is close to 0. So he said, let's approximate omega q mu as an acoustic mode with some velocity c times q, and here q is just absolute value of the momentum. And this is not essential, but for our calculation today, I will furthermore assume that C1 is equal to C2 is equal to C3, and this is just equal to C. So I will assume an isotropic solid. But we could do without this approximation. It's just I don't want to carry an extra index to make it as simple as possible. So we assume this. So in this case, if you make this approximation, you can actually calculate this density of states exactly. And let us do that. So it's just 3 times v over 2 pi cubed integral d3q delta omega minus cq. So what I did, I immediately assumed thermodynamic limit, replaced this summation by an integral using the usual prescription. And the factor of 3 is because I have 3 identical modes with the same velocity. Here you can see if I didn't assume identical modes, I would have 3 expressions like these. And I could calculate each one of them separately, but this is somewhat easier. And this is a trivial integral, which you can easily calculate. And the result is 3v divided by 2 pi squared omega squared over c cubed. Okay. So now, this is not the whole story, right? So first of all, so I did this integral over all over all momenta here. And of course, this is not quite legal because momenta are restricted to the first Brillouin zone. And also this approximation where I approximate the frequency with a sound mode also is supposed to be valid only at a small momenta. So there should be some sort of cutoff. I cannot have my density of states to grow with frequency ad infinitum, because after all, I have only a finite number of modes oscillating in my system. So in fact, what Debye did to acknowledge these facts, he approximated this as follows. So he used this expression, 3v over 2 pi squared omega squared over c cubed for omega less than some cutoff frequency, which today we call Debye frequency in his honor, and then 0 for omega greater than omega Debye. Notice that this makes sense because if you look at that picture up there, for instance, as you go to higher and higher frequency, at some point you come to a cutoff above which there is no state, right? So it doesn't make sense to assume that the density of states just keeps growing when, in fact, in a real solid, the density of states should go to 0 above the highest frequency in that graph, right? So this is a very well motivated approximation. Let me find some more space here. So what is this Debye frequency? This Debye frequency can be actually determined by the following requirement. It's determined by a simple sum rule whose meaning is actually very simple. Okay, so this is what Debye would write. Basically what this says is that, so this is the density of states, right? And I integrate the density of states over frequencies to the highest frequency at which this is non-zero, and this should be equal to the total number of states in the system, right? And since our system consists of n independent oscillators, each of them oscillating in 3 independent directions, then I put that number to be equal to 3n. Okay, so this is what sets my Debye frequency. And again, the integral on the left-hand side is trivial because I'm just integrating quadratic function, right? And it becomes as follows. So this integral is calculated as 3v over 2 pi squared c cubed, and the integral itself is 1/3 omega Debye cubed, and I set that equal to 3n. And from here, I obtain that omega Debye cubed is 6 pi squared c cubed n over v. And let me put this in brackets. And as you can imagine, when you have a Debye frequency, so let me call this Debye frequency. Once you have a frequency that you call after somebody, you can as well define also a Debye momentum, just like with Fermi energy and Fermi momentum and so on. this is defined as k with subscript d, and it's simply omega d over the velocity, and one can express that through that formula as 6 pi squared n over v to power 1/3. And if you calculate the numbers, it's roughly 4 over a, where a is the lattice spacing. And similarly, you define a Debye temperature which is often denoted as theta d, and it's defined by the following relation. So this is the Debye temperature, and what you find is that Debye temperature ranges between roughly 74 Kelvin to 1800 Kelvin. The lowest one in elemental solids you find in crystalline praseodymium, and the highest one you find in diamond. As we will see in a moment, this is actually a measurable quantity. That's why I'm associating it with some actual materials. Okay, any questions about this? So let me wrap this up by finally going back to our specific heat calculation, right? So now we have a model for this density of states, so which is right here. And let's just do some calculations. So let's take this density of states, stick it in, and let's try to extract some of the behavior that we can from here. So back to specific heat. And let's just do what I just said. Let's substitute the Debye result for the density of states in that formula. And this is what we get. So it's a kind of fairly ugly expression like this. This expression can be made slightly prettier by defining a new variable that I call x, which is beta h bar omega. So I perform that substitution in this integral, and this will become slightly more appealing, perhaps. So after that substitution, I get the following: 9n kb, which is the dimension full prefactor. Then I get t over theta d to power 3. And finally, I get my integral theta d over t and the integral looks like this: dx x to power 4 e to x minus 1 squared. Okay, so this is a kind of more appealing expression, which tells us that specific heat has the right dimension of kb. It's extensive, it's proportional to n, and then it has some temperature dependence, which comes from the combination of this cubic factor and this integral here. Okay, so what we're interested in is the behavior of this in low and high temperature regimes. Let's call this integral here as f d of theta d over t, which is sometimes called a Debye function. And what we need to do is to analyze that Debye function and see how it behaves at low and high temperatures. So let's start with low t behavior. And by low t, I mean t is much smaller than this characteristic Debye temperature, which means that xd, which I define to be as theta d over t, is actually much larger than 1. Okay? So in this case, in this integral, the upper bound is much larger than 1, and I can approximate this integral as follows. I can approximate it as integral. So basically, I take it as integral from 0 all the way to infinity, right? Since this is much larger than 1. And then I will check that the part that I'm neglecting is actually small. So let's do that. So it's integral from 0 to infinity of this. And then I have to subtract from this what I added. Now, the nice thing about this approximation is that this thing here is now independent of temperature, right? So I can just calculate it, and I can ask a Mathematica or Maple to do this for me, or look into the tables. And this is just a number in any case, which turns out to be 4 pi to power 4 divided by 15. And this piece, when this xd is much, much, much larger than 1, turns out to be proportional to e2 minus xd, and therefore much smaller than 1, exponentially small, in fact. So I can neglect it with a very high accuracy. And so the behavior, leading behavior, comes from this first term. Looking back at my specific heat formula, I just get this to be a constant. And so the leading behavior then at low temperatures is as follows. Cv at low temperatures goes as 12 pi to power 4 divided by 5, and Kb T over theta Debye cubed. And this is again for T much smaller than theta Debye. Okay? And this has been viewed as one of the great successes of early condensed matter physics, because this is precisely the temperature behavior that has been observed by many in basically any solid at sufficiently low temperatures. You find specific heat from the lattice vibrations to go down as a third power of temperature. And for many years before people started thinking quantum mechanically, this was a mystery. Yeah, this is the first result. I think that I finally did it. I ran out of all space here. Maybe not. Is there a hidden blackboard somewhere? Ha! Okay, I knew it. So let's finish this by discussing the high temperature behavior, and then we'll be done for today. By high T, again, I mean T much larger than theta Debye. And in this case, my xd is much smaller than 1, right? So if I look at this integral here, where am I? So I'm integrating from 0 to xd, and this upper bound is much smaller than 1, which means that everywhere under the integral, x is much smaller than 1, right? And when x is much smaller than 1, then I'm allowed to approximate this exponential by its leading term in the expansion. So I just expand e to x as 1 plus x dot dot dot, and just retain the leading term, in which case this f of xd is approximately equal to, from 0 to xd dx, I get x to power 4, 1 plus x minus 1 to power 2, and this is just integral from 0 to xd dx x squared, which is 1/3 xd to power 3. And you can see what happens here. So this xd, once again, is this ratio, and it exactly cancels in this limit this third power of the opposite ratio, right? So in a high temperature limit, I find that the specific heat is just 3n kb to leading approximation, which is also known as the law of Dulong-Petit, which you probably saw in statistical mechanics. And this is a specific heat of a classical So if you employ no quantum mechanics and just calculate specific heat of a three-dimensional lattice oscillating classically, no quantum mechanics, then you would get specific heat that is exactly 3n kb, which is simply the equipartition theorem. You get kb specific heat per degree of freedom, and you have 3n of them, so this is what you get. And this was the big mystery, right? Because people are measuring specific heats of solids. It should just be a constant, but it was not. It went to 0 as a third power of T. That's what they found experimentally at the turn of the century. And this was in blatant contradiction with this classical statistical mechanics. And when you first learn about quantum mechanics, this can be counted as one of those clouds on the horizon of classical physics, like stability of atoms and blackbody radiation and so on. This is one of those things that just classical physics couldn't explain. And so when you then plot as a function of temperature your specific heat of a solid, and this is the classical result, Dulong-Petit, 3n kb, and you actually plot this Debye function, it will look something like this, where somewhere here is theta Debye, and this is the T-cube behavior that comes from quantum mechanical treatment. And indeed, you measure specific heat of crystals, and it looks just like this. Question?
How was historically Debye temperature measured? So people had some kind of the curve for specific heat, right? So where did they draw this line?
Well,
because it's approximate from this.
Yeah. So I don't know historically. I suppose that once Debye came up with this formula, right, then you can extract theta d just simply by measuring this curvature here, because that depends only on, here, aside from universal constants and some numbers, you can extract theta d just by fitting the low temperature behavior, for instance, right? That would be one way. So what I will do next time, I will set up a projection system and show you some of the actual measured specific heats, and we will then actually see that this is how they behave. More questions?
So here, in the last calculation, we neglected the term of the numerator.
Yes. So I'm just going, in the numerator, I'm just using this 1 on the account of this x being much smaller. In the denominator, I cannot do that because then I would just get 0 in the denominator, right? So I'm expanding to first order. Question? This is only the contribution from lattice vibrations. There's, of course, contribution in metals from electrons, in magnets from magnons, and so on. So you would expect behavior like this in non-magnetic insulating crystals. It turns out this is still the largest contribution in most solids. Even in metals, if you include electrons, and in magnets, if you include magnetic degrees of freedom, it mostly looks like this overall, although there will be some deviations at very low temperature when these other degrees of freedom become important. Yeah. Other questions? No? Thank you very much then. Well, I see you all tomorrow.